Section 3 point, let's see, 3.1, 3.2, 3.3, 4. I believe it's 3.5, double angles and half angles. This is your lesson for that. So if you are, or if you can get the worksheets, the guided notes, I should say, that look like this. It starts with recall the sum and difference identity for sine. And we will begin. So the objectives of this lesson, by the way, are to establish what the double and half angles identities are, and more importantly, apply them in different contexts. So we'll begin. Recall that the sum and difference identity for sine is given right there. Fine, the more I read, the more I kind of mess up, and it's just there. So we're seeing right there the identity for sine. And I'm just reminding us how to structure that. But now we're going to suppose that A and B are actually the same measure. So maybe they're both 10 degrees. They're both 20 degrees. They're both 82.1 degrees. Who knows? Well, we still can apply this identity. What would it look like? Well, all the B angle of rotations would just be the same value as A. And on the left-hand side there, we would have, therefore, the sine of 2A if you simplify the expression. And on the right-hand side, I'm going to pause this here. On the right-hand side there, what you're seeing is, so you have sine A times cosine A, and then you have plus cosine A sine A. So I really want to focus at the end of that, that last term, cosine A sine A. That's cosine A times sine A. Multiplication, you can switch the order, right? It's commutative. So imagine in your mind that we switch the sine and cosine A. So I'd be looking at sine A cosine A plus sine A cosine A. Hey, those are like terms. I literally just said the same thing. So we can combine them to make 2 sine A cosine A. And that's it. This is called the double identity or double angle identity for sine. The sine of twice an angle is equal to 2 times the sine of that angle multiplied by the cosine of that angle. And there are other identities. There are other double angle identities for sine, cosine, and tangent. The cosine has 3 manipulations, 3 different ways it can be written. So I'm going to ask you to use your book on page 198 to copy them down. There are a total of 1 for sine, we already got it, 3 for cosine, and 1 for tangent, 5. Okay. Now that you've copied those down, so at this, let me pause my video for a minute, because you should be pausing your video for a minute to find your textbook or go on to the e-text to grab that. Once again, I do realize even still there are been some issues with MATLAB. Even myself, I tried to change some due dates last night. I was getting infuriated, but then I took my own advice. I said, relax. Everyone's stressed out, even all the way up to the people in Pearson at MATLAB, right there. They're dealing with their types of issues. So we'll all work together. No need to get stressed about this. So leave it at that. But what I was saying is take your time now. If you have the hard textbook, copy those down. You can Google this stuff too. So by the way, double angle identities, they're well known, well written about all over the World Wide Web. So just giving you another option to copy that down. But I don't want to take any more video time to just copy stuff. You can do that on your own. Here we go. Now we're going to apply the double angle identities. So the first thing I need to be able to do is write this as 2 times an angle. Well, 90 degrees is 2 times some angle. I mean, I don't even really need to show my work. I'm just doing what's in my mind. 90 is 2 times 45. So therefore, so that I am able to structure this into a double angle, I'm going to write sine of 2 times 45 degrees. I'm replacing 90 with 2 times 45 degrees. And now I'm just applying the identity. So the identity is 2 times the sine of A times the cosine of A. And in the next step, I'm about to evaluate the trig functions sine 45 degrees and cosine 45 degrees. And then what will follow is arithmetic. So I want to pause there for a moment. The directions were to apply the double angle identities to evaluate the sine of 90 degrees. And this is a nice introductory example to structure the process of doing it. So we were given 90 degrees. First, I need to write it as 2 times a value. Obviously, that value is 45 degrees. Once I'm able to write that, I structured it in line 1. Then I applied the identity in line 2. And then I evaluated the trig functions in line 3. And then lastly, to get the value of 1 from line 3 to 4, just arithmetic skills. Now I want to step back here and say, I would never calculate the sine of 90 like this. Never in my life. I only did it because the directions asked me, and I'm a good little sheep. But no. What this really should be titled is like verifying that the identity holds. But we would never in mathematics, no one does this, right? We're just verifying something we already know is true. How do I know that the sine of 90 degrees is 1? Yes, you're right. I heard you out there. Look at the unit circle. Rotate 90 degrees. So you're terminating on the positive y-axis. The sine is the y-coordinate. So at where it intersects the unit circle or along the unit circle, 1. So that's the easiest way to calculate sine of 90 degrees. It's 1. But we just verified that the identity for double angle holds. And I can already see in the next example, cosine of negative 3 pi over 2. I would just use the unit circle. Rotate. Negative means I'm going to rotate like a clock. Pi over 2. So that's down to the negative x-axis. Let me start. I'm on the positive x-axis, so if I rotate like a clock, I'd be at the negative y-axis, then at the negative x-axis, and then finally 3 pi over 2, I'd be at the positive y-axis. And the cosine there is 0. Okay, so let's see if this actually holds 0. So first I need to write the angle as 2 times some value. Basic algebra here. I can divide by 2. Personally, I didn't divide by 2. I multiplied by 1/2 because I didn't want to deal with fractions on top of fractions. So if I multiply both sides by 1/2, I can easily see negative 3 pi over 2 is the same as 2 times negative 3/4. Just like in the last example, line 1, rewrite it so that we can apply the identity. Line 2 is to apply an identity. Now, this is a good time to say, well, Mr. Alowitz, there were 3 different choices to use. And I would say you're absolutely correct. Why did I choose this one? Because it was my favorite. Now, there will be future opportunities or future problems where there is a better choice over another, but just take a chance, right? In this case, it really didn't matter. You wouldn't have known that, but if I almost encourage you to do one of the other remaining identities, not the cosine squared minus sine squared. Use one of the other identities, you'll still get a value of 0. Last example here. I was kind of talking through while I was writing that out, but so for tangent, same structure. We need to find the value of A so that we can structure our trig function to be able to apply the double angle for tangent. And now we apply the double angle for tangent. I'm just going to give this a little kick up here. All right, so move it along. Little typo there. So after substituting in, now I'm evaluating. Tangent of 2 pi over 3 is negative square roots of 3. You have the same value in the denominator. And at this point, I'm just doing arithmetic, just arithmetic from here on out. And you have a factor of -2 that cancels very nicely there for a final answer of square root of 3. That's my issue right there. Don't worry about that. That's on me. When I was typing this up, I kind of zoomed on the screen. So, all right, moving on. Now we're going to find sine, cosine, tangent, cosecant, secant, and tangent, given that the cosine of twice alpha is 1/3, and that 360 degrees is less than 2 alpha is less than 450. Okay, I've read through it. Now, let me ponder this. Find cosine. Well, let me read it in order. Sine alpha, cosine alpha, tan alpha, cosecant alpha, secant alpha, and tangent alpha, given cosine of 2 alpha. All right, number one, I realize what I have to do here. I need sine, cosine, tangent, and their reciprocals for. All right, identify what I need to answer. What's given to me? Well, I have a trig fact, but it's cosine of 2 alpha. It's double alpha. All right, well, that's nice because this section is called double angle identities. And we have some information about double alpha. We know 2 alpha is, let's see, greater than 360 and less than 450. If I travel like a circle and a little. So this is an angle. Double alpha is in quadrant 1. I don't know if that's helpful. I'm talking out loud. It is what it is right now. All right. So with no further ado, let's do it. I understand what I need to do. I got to find the 6 trig functions for a single alpha, but I'm given information about double alpha. So let me apply an identity. So on the left-hand side, I chose to use the form 2 cosine squared alpha minus 1 equals 1/3. Why did you do that, Professor? How did you know to do that? Well, I want to find one of the 6 trig functions. Actually, I want to find all 6 of the trig functions. But I know what I'm asked to do in this is find sine, cosine, tangent, yada, yada, yada. So my thinking, my rationale was the identity that used sine and cosine wouldn't be helpful. I don't want to still have 2 trig functions to work with. I wanted to be able to get down to one or the other. So I would say I could have wisely chosen the identity that includes sine squared, but I didn't. I just stuck with cosine squared, but it wouldn't be incorrect and you would get a nice answer. But I would say here's a situation where you want to be able to kind of understand why I chose what I chose here. It's definitely more reasonable to choose an identity that only contains one of the trig functions. So once that substitution was made, I added 1 to both sides to make 4/3. So we have the given, I made the substitution, I added 1 to both sides, basic algebra here, right? So I thought of this in my mind as 3/3. When I add that to the other side, it becomes 4/3. Now I need to divide by 2. Looking and seeing a fraction here, I get nervous, so I don't divide by 2, I multiply by 1/2. That's pretty easy. This becomes 1/3. I'm sorry, I don't know why I say 1/3. I'm looking, when I divide by 2, 4/3 becomes 2/3. I'll multiply by half. And now to get rid of the squaring, I take the square root. We get plus and minus. And I think this is a good opportunity just to check in. So everything in black so far is just basic algebra. Now, I have, using basic algebra, when I take a square root, we have a plus and minus. So now I need to figure out what sign should I choose? Cosine of alpha. Well, going back to the given information that I have highlighted in mustard yellow, we're given information about 2 alpha. Using basic algebra here, if I divide everything by 2, I can find information about alpha. Alpha is less than 225 degrees, but greater than 180. That means it's in quadrant, and I paused the video. That might be deceiving. It is not quadrant 1, but quadrant 3. So alpha, we know, is in quadrant 3. Interesting. And in quadrant 3, we know that the cosine is negative. So ultimately, I now have the cosine of alpha is, and now I'm just doing rationalizing work, negative square root of 2 divided by square root of 3 after rationalizing becomes negative square root of 6 over 3. And we found one of the trig functions we were asked to find. I can immediately invert it to find the secant using the reciprocal identity. So now I have 2 of the 6. How can we find the remaining 4? Fall back on the Pythagorean identity, that cosine squared plus sine squared equals 1. I'm going to make the substitution from using the answer I found previously. And I'll probably just give this a little kick here because at this point it's basic algebra. I'm subtracting 6/9. I'm taking a square root. That really should be plus and minus. There we go. But we already know that alpha is in quadrant 3, so I can ditch one of the signs. In quadrant 3, sine is negative, and we're done. What can I immediately find if I know the sine ratio? Invert it, take its reciprocal, and you immediately have the cosecant. Do a little rationalizing. And now we're down to finding 2 more remaining values. We need to find the tangent and cotangent. Pause the video. What would you do here? How would you do it? There's not one correct answer. There are many ways to find it, but I'm going to show you what I think is the most elegant, the quickest. Tangent is a ratio of sine to cosine. We found a moment ago that the sine is negative square root of 3 divided by 3. A few moments ago, we found that the tangent was negative square root of 6 over 3. And here comes some arithmetic for you. So I'm showing my steps so you can reproduce this and hopefully understand everything that I'm doing. And just like that, we have the tangent. So I didn't say anything there, just let you observe the arithmetic. And once we have the tangent, we can find the cotangent. You can take any reciprocal you want. Okay, you could reciprocate anywhere along the way, but I just quickly noticed that if I reciprocate the 1 over the square root of 2, I would avoid hard work. And I don't know. That's it. So we're done. The 6, we found all 6 trig values. Wasn't too hard, just time consuming. But it's a nice question in trigonometry for sure. So now that we've established the double angle identities, you can manipulate them to establish the half angle identities. But I'm not actually going to do any proofs. I'm not going to do the derivations of them. If you're a mathematics major, you're probably the only group of students that really care about why they work. Physics and science majors more just want to know what they are, study them, and be able to apply them. And if you're in here for another reason, you probably don't care about either, except just getting a good grade. Good grade. But it is kind of interesting to see their derivations. Even if you are like in here for whatever reason, just to say, well, all right, how did you get that? It's just algebra. So if you go to that link and watch the video, I believe it's no more than 5 minutes for sure. It just shows you how you can manipulate something you already have into something you need. And I think that's a nice problem solving skill, regardless if it's trigonometry or math related or not, right? It's trying to deal with, all right, how I have this, how can I manipulate it to that? Now, granted, in this situation, it's very procedural, but I digress. I'll just go back to the lesson. So now that we've established the half angle identities, let's apply them. So the directions are to find sine, cosine, and tangent, given the sine of a half angle is -1/3. And we have some information about what quadrant that in. So this already has a feel to me like the last question we just did, right? Except now it's with the half angle identity. So I immediately began this by writing what the half angle identity for sine was. Again, you can copy those from your book. And what I'm stressing here is that the half angle is I lost my track here. So the half angle is in quadrant 4, which means sine must be negative. So I started by writing the identity, and the identity has the plus and minus sign, but I needed to ditch one of those. In quadrant 4, sine is negative. And let me just pause this to make sure that we're clear. All right, so line 1, apply the identity. Second kind of reasoning was figure out the plus and minus sign, but I did that and I just explained that. So now from line 1 to line 2, I substituted on the left-hand side the actual value that was given in the opening information. And the right-hand side, I didn't do anything. And what's about to follow from here is algebra. I'm going to square both sides to clear the square root on the left. I'm going to cross multiply and go from there. So you have an outline of what you're about to see. So from line 2 to line 3, I squared both sides. From line 3 to line 4, I use cross multiplication, cross multiply, making sure you distribute the 9 into both those terms. Now I'm just applying basic algebra steps, subtracting 9 on both sides, and then dividing by -9. And we have the cosine of alpha is 7/9. Which quadrant are we in? Wait a minute. This is cosine alpha, and we have information about alpha over 2. So I need to multiply that inequality by 2 throughout to find out information about alpha. And by doing that, I end up with 7 pi over 2 is less than alpha is less than 4 pi. This was late at night, so you're literally seeing my thinking process here. I'm like, all right, 4 pi is there, 7 pi over 2 is over there, so the angle's still in quadrant 4, which means cosine is positive. And I'm done. Cosine of alpha is 7 pi over 9. I think it's worth noting that pay attention. You might say, well, you were in quadrant 4. Why are you checking again? Alpha over 2 was in quadrant 4. It's worth checking to make sure that alpha is still in quadrant 4, because I mean that I want to say still is. It's that could change at any time. Okay, so that's not a good assumption to just say, oh, it's going to remain. Do the algebra that I did to find out the information. Even though I was just talking, you can see the steps to find sine. We use the Pythagorean identity again. It's just common practice in trigonometry. If you have cosine or sine, you can find it's one or the other, vice versa, using the Pythagorean identity. So if you need to at this point, pause the video and kind of just check out the steps. I'm not going to give any more wind. I'm not going to talk about what I did there. Just we've seen this enough now. But I'll just summarize it that I've applied the Pythagorean identity to find sine. We're remembering that alpha is in quadrant 4, so sine is negative. And similar to earlier, to find the tangent, there are a few ways to do it. The most direct is to call, especially since you have information on sine and cosine, is to use the ratio. Substitute in your values, simplify, and you're done. And we're about done with this lesson, so hang in there. I know we're about 26 minutes in. I'm going to end with I believe it's two examples that ask us to take a expression and apply algebra or geometry or previously established rules from trigonometry, or anything you already know from your mathematics toolkit that you can legally do to get it into the form that's asked for. Now, section 3.2 in our textbook is called verifying identities, and we're in a way doing that. So for anyone who's had trig exposure before and you've verified identities, you're more familiar with this. If you've never had a trig course, it's a pretty common practice to do in trigonometry, but I had to make a decision about what to cut and whatever. I won't bog this down. So I'm still incorporating the ideas from 3.2 into lessons. I don't know. That's my little rant. Commercial break. Professor, just finish up, please. Okay. So show that the expression cosine to the fourth y minus sine to the fourth y can be rewritten as cosine of 2y. My last little blurb here. Basically, this is you want to be able to say, all right, what algebra can I do to that given expression to make it look like what's asked for me? Mentioned this a few times. Super ridiculously important for concepts in calculus. All right, with no further ado. So what are you thinking? Cosine of the fourth y minus sine of the fourth y? What algebra do we know? Hint, factor. That's a difference of two squares. So just like you would factor x squared minus 4 as x plus 2, x minus 2, same reasoning, difference of squares. Now, our first group there, oh, I mentioned it. Hey. Now, where can I go from here? Many, many steps, legal things. But I notice, hey, cosine squared and sine squared, that makes 1. So I'm going to apply the Pythagorean identity and call that 1. Why? Because I have 12 years of experience and I've taken too many trig classes to know that's what I should do. That's not an obvious move. So if you're wondering, why would I do that? How did he know to do that? Exposure and practice. And this is a big key step, so I don't want to rush it here. So I call that factor 1. And so I'm just backing up here. So then we would carry on the group of cosine squared minus sine squared, which I did. And then how do I go from there? Well, a common practice is to say, I want to be able to get to cosine of 2y. How can I possibly do that? Well, let me see what cosine of 2y looks like. And son of a gun, when I did that, it looks like exactly what I have here. So if you look at the double angle identities for cosine, this is one of them. Cosine squared minus sine squared is a double angle identity for cosine. So that's it. My final step was to say, I did it. But I'm going to show you that I did it. I'm going to take one final step here and show you. And when I say show you, show the reader that I was able to do it. That right there is equivalent to the cosine of 2y. And we're done. It's called verifying an identity. You start with what's asked and you manipulate it using legal moves, legal algebra, legal substitutes, and so on. So now you can read this on your own. We're going to show that 2 sine squared of u over 2 is equivalent to that expression over there. So immediately I challenge you, what would you do first? Even my thought process, I was like, I'm not really sure. I think I made a mistake here. Let me rethink this. So I believe I'm about to show that I'm going to start with the half angle identity because it says start there. So I'm starting with sine, even though we're given information about, or it says u sine squared, but I'm going to start with sine of u over 2 and write what it's equal to. So that's literally the half angle identity. And then I said, hey, I can square both sides to make sine squared. So basically what I'm doing is saying it's like a Lego block. I want it to look like this. I'm starting here. So now I'm going to square both sides to get sine squared. And now I'll double both sides to make 2 sine squared. And I think this is a fundamental understanding here that what I've just done now was be able to take what was given to me and find an expression that it's equivalent to using the half angle identity and squaring and doubling. And now we're here. We're here. We've showed that 2 sine squared of u over 2 is 1 minus cosine u. So that's just what I was able to get using the algebras and identity. And now I got to look at the end game. I need to make this look like sine squared u divided by 1 plus cosine u. I need to show what I have circled in red there, 1 minus cosine u. I have to come up with algebras and strategies to make it look like sine squared over 1 plus cosine u. How am I going to do that? Oh, very wise. Whoever said to multiply by 1 plus cosine u is a genius. Because if I was in your shoes, I wouldn't have thought of that. But in all seriousness, here's the main point here. What I'm being a little bit silly, but I'm going to be serious. A common strategy that's taught to students is sometimes that you're like, I literally role played, like, how am I supposed to get here and make it look like that? I don't see any factoring. I don't see any difference of squares. I don't see like a substitution that's very obvious. So sometimes looking at the end game and saying, I want it to look like that. What could I how could I get there? And again, it takes practice. But a big clue to me is I eventually want a 1 plus cosine u in the denominator. And again, here's the cleverness about how to do that. So let me just wrap this up. But I wanted to stress, these are not always easy, but I'm peeking at my final destination, and I want to point out the fact that I notice I want a 1 plus cosine u in the denominator. I can legally get that by multiplying by a form of 1. So this is pretty darn clever. This is clever. I love it. Boom. I take the expression and I multiply it by a form of 1 as written. And now I have a 1 plus cosine u in the denominator. Yay, because that's what was asked. And in the numerator, I have to expand the 2 groups. And when I do that, I get 1 minus cosine u squared. And if you manipulate the Pythagorean identity, that sine squared plus cosine equals 1, if you subtract cosine, you get sine squared is 1 minus cosine squared. So we can substitute that. Let me just back that up. Important thing to really observe and kind of just walk you through. So what's written in green was multiply by a form of 1. And again, that was pretty clever. Years of experience, but the more I'm transferring that knowledge onto you guys, it is pretty cool. In the numerators, you expand, you get a 1 minus cosine squared. And you can use the same argument. I need that to look like sine squared. And I've given this hint before. I have something with cosine squared. I want something with sine squared. I mean, that's screaming at me to use the Pythagorean identity. So I wrote it to the side and I said, if I subtract cosine squared from both sides, we can always substitute sine squared with 1 minus cosine squared. Yay, because we have 1 minus cosine squared and we want sine squared. So that's the rationale there. So that pretty much, that does cover lesson 3.23435, double and half angles. And have a wonderful day. Please email me with any comments or questions or concerns. Take care of yourself, and I'm going to wash my hands. Hope you are too. Take care, guys.